Okay, so I think we'll go ahead and get started here. Hello, and thanks for joining us. I'm Steve Reinhardt, VP of Product Development at Quantum Computing, Inc. And I'm going to talk today about our technical direction and give a brief demo of one of our products. Today's session will focus on high-level technical issues, so not so much on business aspects of QCI or deep technical depth. We'll cover those in future webinars, so if there are particular things you're interested in, please let us know. Also, during the talk, if you have questions, you can send them via the Q&A thing I just mentioned, or you can also send them to info@quantumcomputinginc.com, which can be a fair amount to type, but alas. Okay, so let's jump in. So what are we doing here? QCI's mission is to enable the creation, testing, and production use of quantum-ready applications today. So there are two keywords here that phrases that deserve some definition. One is quantum-ready. What do we mean by that? So that's developed using methods that map directly to quantum computers. No application level changes would be required to execute on a quantum computer. Our tools, we know how to have them execute on quantum computers, and so that's essentially our job, not your job.
Hey Steve, you're currently talking ahead right now. If you want to switch to the presentation.
Oh, thank you. Yes, I did want to do that. Thank you, Jason. Okay, sorry about that. So, quantum ready is a big piece of what we're doing. Another big piece is today. So this means you have access to these quantum ready applications. We also do tools underlying the applications. That means you can get access to them today, you can get benefit today. We believe this will do two things. Number one, accelerate the production use of quantum computers when they deliver advantage. That is still in the future. Also, that's likely to happen in hybrid quantum classical modes. And so we think it's really important to start on that now, because getting that right is not going to happen overnight. Another thing this enables us to do is to broaden the range of applications that will be able to take advantage of quantum computers, because there's a stable base to build on to build those quantum computers. Quantum apps. And the last thing I'll mention here is that our middleware, we call it Mukai, it's available in the cloud today. So when we say today, we really mean today, Tuesday, April 28th. So you can log in today and start to get benefit. So a very important context for what we're doing is, when is there going to be performance impact by quantum computers on real world problems? And there's a tremendous amount of discussion about that and when that might happen. Well, this is my view. The first time that might happen is maybe sometime next year, maybe into the next year, for the next generation D-Wave system called Pegasus, internally dubbed Pegasus. That's one point at which we might get quantum advantage. The next possible point is for non-error corrected gate model quantum computers. So these are the ones being built by IonQ and Rigetti and Honeywell and Google and IBM and many others. So that might come about in roughly 2024. So that's 3.5, 4 years from now. These estimates have significant error bars on them, but that's when that's a plausible time at which we could get quantum advantage. If we're not able to, we, the community, are not able to figure out how to use non-error corrected gate models, then, and we have to wait for error corrected, then that's like maybe another 8 years or so. So that puts us out to 2032 plus or minus, which is quite a while to wait, obviously. So these are my estimates. These could be wrong. If you have your opinions, tell me about them. I'd be happy to talk about that. It's important to call out that these are the dates when the hardware is available. And if we're not careful, the date when hardware plus software plus the apps that you care about in your business are available could be substantially later than this, years later than this. Another important thing that we take away from this picture is that many organizations, even ones wanting to be quantum forward, they look at this and the uncertainty of the quantum advantage date, and that's a reason to delay spending. I mean, if you can't tell when it's going to have advantage, the easiest thing to do is nothing, is just wait. And so a big part of QCI's strategy is we want to give customers reasons to move today to these quantum ready formulations. So the first leg of our technical strategy is that the arrival date of quantum advantage is uncertain. We need to insulate application developers and users from that uncertainty and effectively bring that forward. Next thing is that middleware and/or applications must hide enough detail about the computer for people to get work done. And in the classical world, it's easy to kind of lose track of how much stuff there is down there that if I'm an application developer, I can remain blissfully ignorant about. So there's obviously things like the processor microarchitecture, power management, BIOS, the Linux or whatever other OS you might run. You've got compilers, you got medium level languages like C++. We got libraries like Scalapack. These are all in a metaphor I learned from Jack Worlton of Los Alamos years ago. These are in the iceberg metaphor. These are below the waterline. These are things that application developers don't really want to have to think about. They just do the right thing, get the right answers, don't make me think. Above the waterline is where application developers want to engage and users want to engage. And so, some of the things in the classical world that are there are, there's programming languages like Python and R and MATLAB and the MATLAB environment. Things like SQL for doing database queries. There are all kinds of solvers. There are Cplex and Gurobi and other solvers for combinatorial optimization problems, which is something we'll talk about. Another interface is NetworkX, which is used to solve graph problems. Almost anybody who uses a computer probably has some familiarity with Excel. If you're doing simple kind of spreadsheet type calculations, it's a great tool. I don't have to know anything about the computer. I just get to stand on the shoulders of all those great people who have done that all that work underneath. Tableau is another kind of expert level, high level interface to computers. So in the classical world, we just have these things. They've grown up over 60 years. We're used to them. They're good things. They make us all way more productive. When we look at the quantum world, it's way different. So we see down here that we have instruction level APIs. Every quantum computer has one. Some of them are similar to each other. Some of them are not so similar to each other's, which creates issues of its own. There are low level issues like embedding. And then there are things that we wish were there but aren't yet. Things like error correction, things like decomposition. The early quantum computers are going to be too small to run a whole real world problem. So we need to take the real world problem and pull out a piece of it that we can solve on whatever chip we have today, and then take the results of that, meld those back into the whole problem and solve the overall problem. That's going to be really important. We have some, early work on that, but that really needs to be done. Similarly, simplifying and reducing problems is something that classical compilers are great at. They do a tremendous amount of that. We don't know so much about that on the quantum side. So where we have focused our attention is primarily above the waterline. So kind of, again, continuing on our road up the stack to above the waterline. So we have a QBO solver. A QBO is a particular mathematical form, quadratic, unconstrained, binary optimization. You may have heard of this, may have not. If you're an application user, it doesn't really matter. We have a very good solver for that. And that's one of the APIs that we expose today. Another one is NetworkX, which is for analyzing graphs. I'll come back to that in a few minutes. Another one that we see a lot of promise for is an end user application. And this is QAA, we call it, Quantum Asset Allocator app. So this is intended for fund managers in the financial world who want to optimize their investments over a significant set of investments, and they have particular constraints. You know, I don't want more than 5% of my funds in any particular instrument, or you know, I have to have a certain diversity, or you know, following factors, et cetera. So that's a way that you can actually be a subject matter expert in something completely devoid of quantum computing, and you can use a quantum computer and be blissfully ignorant of those low-level details. So this is one thing that we think is really important, is to hide an appropriate level of detail. Another thing we're doing is moving towards something that's a little more general than a QBO solver, which would be a constrained optimization solver. So constrained optimization is, so, you know, UPS, FedEx, all these package delivery systems, logistics companies. One of the problems they have is you're going to send a delivery truck out. You want to put into it the things that are highest value to your customers, and will get you the most revenue. You want to make sure that it fits. That you want to take a route that is as, you know, close to short as practical, and that you don't spend too much gas, and probably some other, you know, you probably have other constraints that I'm not thinking of. So, and within that, within those constraints, you want to do the problem as quickly and as efficiently as possible. So that's a constrained optimization problem. Solvers for that are very well known. And so we'll be generalizing to that constrained optimization step over the next few months. We're not ready to talk about that yet. Probably another webinar when we are. I don't want to imply that we're the only ones doing anything above the waterline. There's TensorFlow Quantum is, for those of you in the machine learning world, TensorFlow will be something you're familiar with. And Quantum is actually, is obviously a way to use quantum processors for that API. So another pillar of our technical strategy is we need to insulate application developers from machine-specific details. Things like the number of qubits, the topology, the gates that are supported, et cetera, et cetera. So another leg, as I mentioned earlier, is delivering superior performance today. If we're going to get people to actually move in earnest to using quantum-ready formulations, they have to have some reward. They're not just going to spend money with no reward. Okay, so how we do that? So there's an important thing as we go from the classical world, especially the HPC world, to the quantum world. Performance is a more diverse thing than it was. You know, in the HPC world, we think about a specific sequence of operations. You know, I know I'm doing 64-bit floating point. I'm doing this, you know, adding these things together, and I can know how many operations that is. And so once I know how many operations it is, I just want to do it as fast as possible. So when we think about speed in the classical world, it's almost always operations or floating point operations per second. Because we know however we do it, we're going to get the same answer. Well, in the constrained optimization world, and in many areas that are going to exploit quantum computers, that's not quite so true. And so the quality of an answer, you know, to go back to our delivery truck packing example, if I'm packing a delivery truck, what's the best I could possibly do? Well, to calculate that exactly would take, a classical, a very large classical computer, the lifetime of the universe to figure that out. So no one's going to do that. They get an approximation. They say, oh, that's good enough. We'll go with it. Well, if you can have an answer that's a little bit better, that might be valuable to you. Again, very context specific, but that might be valuable to you. So the quality of the answer is the first dimension of performance. Speed, still, I get this quality of answer. How long does it take me? Another dimension that's new for many people from HPC is diversity of answers. So again, the delivery truck packing example, there might be 50 different ways of packing the truck that are almost exactly the same. But some of those might wind up with a layout that is much more stable. And if the truck goes a little faster than we're expecting, it's less likely to jiggle around or break anything or have anything fall on the floor. So that might be something that you don't actually specify in your solver, but you as a human looking at those results, you might say, oh, this result is actually a little bit better than this one for some other reasons I didn't actually call out. So diversity, we hear lots of places, is really valuable. So with that caveat that there are all these dimensions that are important, for this particular plot here, we're focusing just on the quality of answers. And I should explain my plot here. So MQLib is a library that's put together out of MIT about 5 years ago. It's a few thousand QUBO problems. And we selected some of the hardest ones from that. I mean, the longest running and the ones where only one of the heuristics they tested gets good answers. So we selected 45 of the hard ones out of MQLib. And there are other people we've talked to who are also focusing on those same 45. And so we ran those with our Mukai QUBO solver called QBsolve, QCI QBsolve. And here's the quality of answers we got. I should also call out on the Y dimension, is the relative energy value. And so this is, in the MQLib world, they ran a bunch of stuff and they got the best answers. And so this is looking at those best answers and where we are, but it's only relative. So if they got an answer of 2,814 and we got and bigger is better, and we got an answer of 2,815, that's what, 1 part in 2,000 better. So it's, that's only a little bit better. If they got 2,814 and we got 3,000, well, that's a bigger difference. So and different problems have different energy values. So we've made them all relative to the baseline. And then as you can see, this is a log chart. So there are some of these that are much bigger. Sorry, let me say that. There are some of these that are just tiny differences, and there's some of these that are bigger differences. Those differences, the value of those differences are application specific. So what you see here is that compared with all of the heuristics that the MQLib people tested, there's 37 if I'm remembering correctly. If we go from the left, there are, I believe it's 15 of the instances that do better in the other heuristic than we're able to do with QCI QBsolve. There are 9 with which we tie, and there are 21 where we are better than all of those heuristics. So this is pretty good. This is a set of hard problems. We're pretty pleased with this. And this is one of the ways that we can say to people who are solving these combinatorial problems that QUBOs do well, is you should be adopting this platform now, because it does give advantage. And I want to be clear, people have an expectation for quantum computers that is way bigger than 10 to the minus fifth or 10 to the minus third. They're thinking 1,000 times better, 1,000,000 times better, and not necessarily on energy value, but maybe in speed or other dimensions. And we're not going to be able to do 1,000 times better. This is running on a classical processor. We're just using the classical processor in a different way. But this gets you over the hump of getting into that quantum ready formulation, such that when the 1,000 times or 1,000,000 times is actually here, that it's delivered for a problem you care about. Okay, so the third leg of our technical strategy is deliver superior performance now. The last one is we're going to focus on constraint optimization. I've described that as the delivery truck packing problem. There are many instances of this. It's like, how do you route airplanes across the North Atlantic? How do you route traffic so you have minimal congestion? How do you use parts and repairs and machinery in a factory so that those are as efficient and you get as much throughput as possible? Again, places where huge amounts of money are spent, and just a little bit better answer can be really high value. And like I said, versions of this are now available in the cloud via our website. Okay, so actually maybe pause for a second. Jason, are there any questions that have come in that I could stop here and answer beneficially?
Yeah, so one question that came in was, are you going to make more information about performance available, especially regarding the MQ line capers?
More information about which?
Just performance, right?
Oh,
Especially regarding the MQ line.
Yeah. Actually, we're working on writing this up and submitting this to a conference here pretty soon. So I would expect some more public information about this in the next, I don't know, couple of weeks, few weeks probably.
Other than that, no further questions, but yeah, if you guys have any questions, feel free to shoot them through the Q&A button or email them to us at info@quantumcomputinginc.com.
Okay, cool. So I'm gonna switch gears here and go into a little demo. So I mentioned NetworkX. That's a graph analysis package. Sorry, I'm jumping in too quickly. So a graph, there are multiple meanings for that word. What we mean by a graph is a collection of vertices, points, nodes. They're called various things. Collection of vertices and edges. And edges connect usually a pair of vertices. So NetworkX from Los Alamos National Lab is a well-known package for manipulating graphs. There's a set of graph problems that are very compute intense and are seen as a good, a good first use for quantum computers. Minimum vertex coloring is one of those. So I'm going to give a little example here using minimum vertex coloring. So rather than spend a lot of time defining that, I'm just going to jump into a problem. So imagine I'm a student at a university and I have some classes. And so I'm representing each class by a vertex. And what I want to do, the problem we're aiming at is how do we make sure that the classes, the exams get scheduled so that nobody has to be in two places at one time. So what we can do is we can add edges. So if these are my classes, then I add edges between every pair of vertices to say, and the edge means these should not be at the same time. Because if it is, I'm going to have to be in superposition or time travel or something. So, okay, so these should not be at the same time. Okay, so then we say, okay, let's add another student, and maybe some of those courses are new, and maybe some of them are in common with what I was taking. And so the same thing, the other student, we want to make sure that they don't have to be in two places at the same time. And we add a third student and some new classes and some overlap, and the same thing, they shouldn't have to be in two places at one time. So the question we wind up asking is, which exams could be held at the same time? Well, even from this tiny example, this is only 3 people and I think it's 11 courses. This is pretty busy. It wouldn't be trivial to figure this out with pencil and paper. And when we ask the questions of which exams could be held at the same time, those are vertices that don't have an edge between them, like these two, could be held at the same time. Of course, if we start to circle all of those pairs of things that it could be at the same time, then it gets messy pretty quickly. And again, our human intuition isn't really very useful there. And I will point out that there are even triples of classes that don't have any edges between them, don't have any students taking both of them. So it would be possible to hold all 3 of those exams at the same time. But clearly this is something where, this is getting busy. This is not something that you want to solve by hand. So I'm going to jump out of this for a second and I'm going to switch over to a Jupyter notebook here. And so this is some Python code. You can read a lot of this as well as I can. Some of you may be Python people, some of you may not be Python people. Jason, one clarification. Am I sharing my screen?
You're sharing your screen, so we see the Jupyter notebook open right now with
Great.
the graph
Slide in the background. Okay, excellent. Yeah. So here's a little, this is actually just one function from a Python program. This is how you would, solve a problem with Mukai today. And so here I've hard coded our little toy example. Here's how we would create the graph. And then of course, if you want to solve a real problem, probably better to bring it in from a file. Then we're going to call min vertex coloring, and then we're going to visualize those color groups that we get back. So this is fairly simple, simple problem to solve. Okay, so I'm going to go down here, and obviously I ran this previously, but I'm going to do it again. So we'll run it, and takes a second, and it comes back and it spits out in, which it usefully for the small example here, spits out the text answer. So if we go down here, we can see that I think that's Spanish 890. Here, let me. So we can look at these. Okay, so Spanish 890 and is that CompSci 012? So those are in the first time slot, if you will, color, if we wanted to keep with the nomenclature of the graph algorithm. You see there's no edge between those two. So it's okay to color them the same color. We go to the next one, the history of art 234 and art 456. So where's history of art 234? There it is. And art 456 is over here. Yep, no edge between them. So that's legal. And if we walk through here, here's one that actually has 3 at the same time. So philosophy 789, music 567, and computer science 678. You can see there's no edges between any of those pairs of vertices. So those are all legal to put at in the same time slot, i.e. the same color. I have added in my visualization, in this position, i.e. the first connection in the third time slot, I have added an artificial red vertex just to say, if this would be a violation. If SOCH 234 and Econ 123 had an edge between them and they were in the same time, that would be an error. Now we can go over here and say, here's SOCH 234 and what was it? Econ 123 is way over here, and there is not an edge. So you can see that this was just my illustration that was showing that. So that's what we can do. We get an answer. That only takes a twinkling of an eye. And now I'm going to go down here and I'm going to take a bigger problem. And similarly, I'm going to run that. This will take a second. And so there's actually so scheduling exams is a problem, but it's not clear that anybody would get fired up to use a quantum computer for it. But there are problems just like this that map to vertex coloring the same way that are also high value. One of those, so if I'm a cloud provider, an Amazon, AWS, or a Google, or there are many others, I have many systems that I need to keep up to date. So a thing I have to figure out is updating the software on all my servers. Well, how do I do that? I have sets of things that I don't want to all get updated at the same time. For instance, I have a bunch of DNS servers, domain name system. It's a part of the TCP/IP world. I don't want them all upgraded at the same time, because that would mean that DNS would be unavailable while they're being updated. And similarly, you might have a set of servers that are servicing SQL. Well, you don't want to change them all at the same time. So in vertex coloring terminology, you don't want them to have different colors. And those are the things that I know about as the cloud provider. If I think about a level up, I have customers, and they may have a set of web servers, and I may or may not know that those are all web servers, but I as the cloud provider, but that customer doesn't want me to update those all at the same time. Same thing, they want to be able to do that one at a time so that to the outside world, there's no interruption of service. So in that context, your graph can get really big, and this problem vertex coloring solves that problem, but it can take, it's a much harder problem, and it can take a longer time. So here you can see, this is a bigger problem. It has, if I'm remembering, it has 185 vertices in it. It took us, 50 seconds to calculate. So again, we put out the text answer here, which is good enough, but at 185 vertices, that boggles the mind. So you don't want to just look at that. So here we have a plot of that, and I did this earlier, and I have one to show that will be a little less of an eye chart. And actually, I want to point out something here. See, you can see kind of over on this end that these two plots are a little different. And this is what I talked about earlier with performance, that quantum computers are non-deterministic. They're not always going to give you the same answer. And this is a case where that's true. They're a little bit different answer. So we see that visually in this case. And here you see we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 colors. And here again is my, if we had made any errors, then we would see red bars somewhere between vertices. And that one is the one I seeded it with. We don't see those, so it did the right thing. So this has been an example of using the Mukai service, QNX we call it, that QCI NetworkX, to solve vertex coloring problem and visualize those results. So that was the demo. So I wanted to wrap up, and so QCI software is quantum ready today. and delivers superior performance today. That's running purely classically. We know how to run on quantum computers. They're just not faster today. So we don't use them in a routine way. If this is interesting to you, please feel free to check us out on our website or send us email at info@quantumcomputinginc.com. So with that, I will take any questions.
Hey Steve, Doug Fink sent a question regarding what platforms are supported by Mukai. So it's a three-fer. So the first question would be, what types of computer servers is QCI using for their cloud systems?
So today we are using what we would call fat nodes. So these are nodes that have a lot of cores and quite a bit of memory in them. As to what vendor they are, Intel or AMD or ARM or whatever, we don't really pay much attention to that. It's just whatever's fastest. Does that answer the question, Jason?
Yeah, and so the second question would be, if someone wants to run Mukai in-house, what type of on-premises computer servers would be best?
So we've been focused on web execution, or I should say cloud execution, because that's a good match with the pace of development that we're sustaining, which is very rapid. If it was really important to a customer to run on premise, we'd be willing to talk about that. It would be fat nodes, would be the thing we would focus on. So today we're running, for the last couple months, we've been running on 96 core, 192 gigabyte nodes. Doesn't mean that's the only size we can run on, but that has proven to be a high performance and effective size for us. So that might be a good target. We certainly feel that we could run on bigger nodes. So I'd say, get in touch with us and let's talk details.
The last part of that three-part question would be, if he wanted to run Mukai on a real quantum computer as a test, IBM Q or Rigetti, is this supported today?
Right. So literally today, no. We're a tiny little company, and we are very much focused on how do we deliver value today and how do we get people to adopt today. And we know how to make this run, to make Mukai run to quantum computers. So QBSolve in its prior life used the D-Wave processor effectively. There's no near-term customer value to running on a quantum computer. So we don't actually focus much on that today. We realize that having that capability firmly in the roadmap is important, and we are working on making that available. And we probably have something, into this year, early next year, where you actually could run on a quantum computer, and it will be slower.
Next question would be, came anonymously, due to complexity, is QCI finding marketing, getting the word out to potential customers difficult?
Boy, that's a good question. We have mostly been focused on kind of word of mouth marketing. So several of us are very well connected with certain computing and application areas. And so it's been easy for us to connect there. Our CTO, Mike Booth, and I both spent 4+ years at D-Wave. So we know a lot of the early Cubo-focused developers and application customers. So mostly it's been more word of mouth, and we have a handful of early customers that we're working with. Obviously, we need to scale this up as well. And so I'm not sure I'm the right person to have an answer to the, kind of how we would do with marketing. I think, so maybe one thing I would say is everybody likes the quantum ready story. Quantum ready plus superior performance today is, involves showing the superior performance today. And we are just now at this stage where we're able to do that. And so, we have some papers in preparation for some of the upcoming conferences that will document that superior performance. And we think with that, the quantum forward companies are going to start to pay attention, and they'll realize, like for QAA, quantum forward financial companies are going to realize what we're doing, realize that this is beneficial today. It's not an ethereal, in 5 years or 12 years, beneficial today. And so, that'll be, with that proven, that'll be a better thing.
Next question comes from Majed Savi. Outside of HW or cloud resources, what other resources are required to start working with your middleware? Software, human resources, training, HWV hardware in this case.
Yeah, sorry, could you just ask that again? I didn't catch it very well.
Outside of hardware or cloud resources, what other resources are needed to start working with your Mukai middleware? What are, is it software, human resources, training, etc.?
So, I mean, we have a quick start guide. We have, I mean, like for something like QCI NetworkX, there's an existing body of NetworkX documentation that is very usable. I mean, I've used it for several years. So we don't, documentation is one of those things that has to be good, it has to be clear, but we feel like there's a fair amount out there that talks about the kind of broader problems. What else? So if you're not familiar with creating a QBO, that can be a significant intellectual task. That's one of the reasons why we're moving to this constraint optimization solver, because it kind of removes that that necessity and makes it simpler to pose the problem. We will also offer training and consulting services. That we do that as well. So if you're in a situation where you need that, we can, yes, we're prepared to do that.
Next question would be, would it be possible to describe QCI's involvement in COVID-19 applications and challenges?
Sure. So obviously, pretty much everybody is highly focused on COVID these days. It's just, you can't get away from it. We have a couple different things we're pursuing. So one is one of our senior people lives in a small city in Western Tennessee. We've been working with them, with the mayor and the people of the county. So this is Jackson, Tennessee, and just working them on what problems are they seeing, how could we possibly help. We have access to smart device data that can enable, we believe can be a benefit to contact tracing. So we've been talking with them about how that might be useful. That's kind of near term and more tactical. A longer term and more strategic thing is we're working with our technical advisor, Michael Liebman, and we've actually been working on this since the fall. This was before COVID-19, on community detection. And this is, and we see this as very high value in the COVID-19 context. So, there are many people falling ill during this era. Some of them have COVID-19, some of them don't. The ones who do, they have very different sets of symptoms sometimes. And so to pull apart what those different communities of patients look like, and do they have differences about how they contracted the disease? They have differences in the course of the disease. Is it longer or shorter? Are they contagious earlier or later, or for shorter periods of time? How well do they recover? How serious are their damage from the illness? No one knows. I mean, this is happening to the world in real time. And so we have a community detection model that we're working on, and we're talking with some external groups about applying that to COVID-19 data. So that's not an immediate thing. It's not going to be done this week or this month, but that's a thing where we really see high value to that.
So last question, if anybody has any further questions, feel free to submit them using the Q&A button. But the last question is QCI focusing more on government applications and uses or the private sector?
I guess I would say yes. We're not really focusing on one or the other. And we're talking with, if you think the groups we're talking with today, we have one government organization, 2, 3, one government or one commercial organization we're talking to about logistics, one we're talking to about protein folding, one we're talking to about finance. I'm drawing a blank here. Oh, and and actually there's another government agency we're talking to about kind of logistics types problems. So it's across the board. There's no real separation. Okay, so it sounds like that's all the questions we had. So thank you much for taking time to join us. I hope you learned something. Again, if you have questions or suggestions for later webinars, by all means, let us know. And we hope to talk with you again shortly. Thank you. Bye-bye. Stay safe.